Hi, this is Jonathan Gardner. We're covering section 613 in Griffith's Introduction to Electrodynamics, second edition. In this section, we talk about how magnetic fields interact with atomic orbits. Okay. Previously, when we studied the paramagnetic effect, where the magnetic dipole moments align with the magnetic field, we were talking about electron spin. So the electrons themselves have a spin quantity. It behaves exactly like almost a perfect pure dipole. Even when you get close to that electron. And we found that the matter that has an odd number of electrons per atom or per molecule tend to exhibit this paramagnetic reaction to magnetic fields, whereas matter that has even number of electrons tend not to, because they have spin up and spin down, both behaving in the appropriate way. So as we study I guess the best thing to start with is just to really clear up in your head what's going on at the quantum scale with atoms, and for lack of a better way to explain, and you should know that this model is not completely correct. As you understand more about electrodynamics, you'll understand why. But basically, have a positively charged nucleus composed of one or more protons. It has some charge. In this case, we'll just look at hydrogen with one proton, and then around that you have an electron that spins around. And I should have used blue for that for some reason, but I didn't. And this isn't quite correct, but it gets us very close to where we need to be. It especially helps us understand why magnetic fields applied to atomic orbits has the effect it does. It may surprise you that it does what it does, but so let's walk through. So we're going to say that the electron spins at an orbit of r, radius r. It's a circular orbit. The period that's the time it takes to traverse one loop is going to be 2 pi r. That's the distance it travels divided by the velocity, the magnitude of the velocity. Obviously, the direction is constantly changing. If you were to do the math for this, you would find that this period is so tiny that unless you're dealing with a blink of an eye, I don't know if he literally means 100 milliseconds, which is about, no, not 100 milliseconds, 10 milliseconds, I think is the blink of an eye. You have to blink really fast in order to see the electron at a position. And so really what you get is a current of negative charge flowing around this loop this many times a second. The current is equal to the electron charge E divided by the period, how long it takes to make one loop. The electron charge, just for reference, is, can you see this? Yes, you can. 1.60 times 10 to the negative 19 coulombs. So it's a very tiny charge. Then you substitute in here, 2 pi over v for t, and you get ev over 2 pi r for the current. So that's the current. And then you can calculate the magnetic moment. That's just m vector is equal to minus, because it's a negative charge, 1/2 EVR K. So here K hat is pointing out this way. Okay? And what happened to the 2 pi r? Well, that's the area of the loop that it's covering. Okay? So now we have the magnetic moment that points down. Okay, we have a negative charge flowing this way, so it's like a positive charge flowing this way. So you got to follow the right-hand rule. Now, when you put matter with electrons into a magnetic field, there's a great deal of inertia, of angular momentum going on here. It's actually quite difficult to cause these rotations to change their alignment to correspond with magnetic fields you've projected it to. However, the electron spins. It takes a tremendously small amount of energy to cause the electron to flip, from up to down or down to up. And so it's much more likely that when you subject matter to a magnetic field, that the electrons will flip. And if you ever got an MRI and talked to the MRI technician about what's actually going on, so the hydrogen, you have your hydrogen atoms in the different chemicals that are inside of your body have that free electron that's associated with it. And when they stick it in a powerful magnetic field, they can cause that electron to flip. And then at a certain point in time, it'll flip back. And when it does that, it releases a certain amount of energy that can be recorded. It changes the magnetic field and all that kind of stuff. So it's pretty cool. Anyway, what happens, however, is the speed will react to the magnetic field. So maybe the magnetic field will cause the electron to spin faster. Maybe it'll cause it to spin slower. And how can we possibly calculate what would happen? Well, let's calculate the force of attraction. So the force between the electron and the proton, that's just going to be 1 over epsilon naught, 1 over 4 pi epsilon naught, times the two charges, so E squared. And then you have the distance between them, which is just R squared, because they're doing circular orbits there. Okay, and that's going to equal to mass times the acceleration. Well, so we have the mass of the electron, not to be confused with the magnetic dipole moment. That's going to be equal to that times, where did my notes go? Oh, V squared over R. That's the acceleration that it has to experience. So the mass of the electron, for reference, is, I wrote it down here. Where did it go? There it is, 9.11 times 10 to the negative 31 kilograms. Okay, extremely tiny. When we plug in for the magnetic field, so the force that it's subjected to when you have a magnetic field in there is the electric force, E squared over R squared, plus QV cross B. So that's going to be, E is the electric field, V is the, how did they write this out? EV, the new velocity, times the magnetic field. We're doing the magnetic field perpendicular to the plane of rotation here. So that's going to be equal to MEV prime squared all over R. Okay, so this is the, when we put a magnetic field in there, the force is going to change the velocity it's going to spin at so it can maintain that radius. And so what happens to the velocity when we subject, so we're going to put it in a magnetic field that points up. Where's a nice orangey color? Here we go. There's a deep orange. So we're going to put the magnetic field up. Okay, that's the equation we get. So we make the assumption that the velocity doesn't change that much. So delta V is equal to the new velocity minus the old velocity. Okay, and we plug into here this value right here, so we get M E V squared over R plus E V prime B, mass electron V prime squared over R. Okay, so we get this term is equal to ME, and it's V prime squared minus V squared, which is just V prime plus V, V prime minus V, all over R. Okay, and so we plug in delta V here, and that's the small change here, but actually we're going to assume that this is just 2V. So this becomes times 2V delta V all over R, and then we can solve for our delta V. Delta V is going to be ERB all over 2ME. Oh, this V is, yeah, we're going to say EVB because the V doesn't change that much. So the 2 goes on the bottom, the V's cancel. Yeah, that's what we get there. Okay, so what's happening to the velocity of the electron when we subject it to an anti-parallel magnetic field? Well, it increases by that amount. What would happen if we subjected it to a parallel magnetic field with that magnetic moment? Well, in that case, it would decrease the velocity. Okay, what happens when the velocity increases? Well, the magnetic moment would increase. Let me draw that up here. Box that. What happens when the velocity decreases? Well, the magnetic moment will decrease. And so we find that we have this anti-parallel behavior, which gives us our diamagnetism, where it opposes. So as you increase B, you get a change in magnetic moment that counteracts that. Now typically, the diamagnetic effect is much weaker than the paramagnetic effect in matter. And I think for copper, that even though copper has an, oh gosh, I'm going to say this wrong, skip that, okay? But although the numbers here don't exactly match what you would get if you experimented and measured things, this gives you the rule of thumb that you need to know, that the tendency of the magnetic field is that, you know, if it anti-aligns with the magnetic moment, the velocity will increase and extend the length of this magnetic moment. Whereas if it aligns with the magnetic moment, the velocity of the electron will decrease and the magnetic moment will decrease to match, will increase. No, wait, the velocity will decrease and the magnetic moment will decrease when the B aligns with the M. So that's basically what happens there. All right, thanks for your time.